Okay, now, rise in the level. So that obviously once again is like something that hopefully even like in elementary school you kind of talked about, right? But now we want to get a little deeper. Okay, don't say anything out loud. You're going to answer this question on your paper, but on your own. Okay? Water at room temperature exists naturally as a liquid. Right? We all know that. Carbon dioxide. Thank you. Oh, she was in my last class.
Oh, all right. I'll go find it.
Sorry about that.
No worries.
Okay, carbon dioxide at room temperature exists as a gas. Now, let me define temperature and then you'll answer the question. So, temperature from a chemistry definition is the average kinetic energy, aka movement, of the molecules. So, when we talk about temperature in this class, you should literally think of it as it's the speed, right? How fast the molecules are moving. So, they're at the same temperature, but one is a liquid and one is a gas. Why? Why is that? Okay, right underneath the box is the question, and I want you to write your thoughts down. As long as you answer it, you'll get a smiley face. So just think of something. It could be completely wrong, but I'd rather have it be wrong and try than don't try at all, okay? Why is one a liquid and why is one a gas when they're at the exact same temperature? What claims can you make about that? Set your pencil down when you're done with your thought. All right, while you finish writing, if you're still writing, turn to your table buddy and share with them what you think. Ready, set, go.
Water is
I said it
Okay, let's hear a few, and whether you're right or wrong, you're going to smile face for just being brave. Izzy, what do you say?
I put because water molecules can be like close to each other at easier like energy level than CO2 molecules can.
I love it. So Izzy went to what we know is true. We know that liquids are closer together than gases. So if one is a liquid and one is a gas, true statement. That must mean the water molecules, for some reason, are closer together. Good. Have a smiley face. Tyler.
I thought that maybe because like some elements take more energy to move than others, so it makes them act differently at the same temperature.
Oh, interesting. So like maybe their response to the temperature could be different. Have a smiley face. Harsh?
So maybe it's like since water is polar, the molecules are attracted to each other.
Okay. So going to the structure of noticing, well, their structures are different, right? So that maybe plays a role in what we see to be true. Good. Have a smiley face. We'll get one more date.
Hydrogen is smaller than oxygen, so it can become more dense than carbon dioxide.
So that something about their sizing maybe allows them to get closer together and be a liquid, right? Good. Have a smiley face. If you wrote something down, you also can have a smiley face. If you shared, that means you got two. One for writing, one for sharing. Okay? So, it's crazy. Like, chemistry's so crazy because to us things can be so different, but when you go to the molecular level, it's so simple, right? So here's a water molecule, cute little Mickey Mouse, right? Okay, here's another water molecule. Like literally the difference between gas, liquid, solid. Like that is the difference. But to us, they're very different things when something is a solid versus a gas. But at the molecular level, it's all about their distance. So if something exists as a liquid while something else naturally exists as a gas, there must be something that's forcing them, pulling them to want to be together. Versus CO2 has really no inclination to come together. There's no force bringing them together. Okay? So today we are going to be learning about that force, those forces that exist between molecules, known as intermolecular forces, nicknamed IMF, if you look at our objective right there. So an IMF is the force between two molecules. We just came off our unit learning about the forces within intramolecular forces, which is like the force of the H to the O. Now we're learning about the force between them. Now I nickname it the friendship force because molecule, they're friends, right? Versus trying to rip off the actual arm of the individual. Okay, very different forces we're talking about. The true bond versus friendship bond. But it is still a force and it still causes all sorts of things to happen. Okay? All right, so let's jump in and we're going to do a quick review of what we talked about last unit with ionic, covalent, and metallic, and then we'll dive in to the covalent side of things. Okay, come on, you. There you go. Okay, so as we're looking at solids and visualizing them, once again, you've got to get to the molecular side of things in this unit. It is huge, right? Seeing what do they look like at the molecular level. There's two types of ways solids can stack. They can stack in a very organized way, which we call a crystalline solid, or sometimes the stacking is a little more haphazard, right? And those are classified as amorphous solids. So just kind of when we look at two different solids, ionics are typically always crystalline. Metallics can be a little bit of both sometimes, and then covalents as well. Izzy?
What's the, like, how does it look different, like, from our eye, like,
Oh, like to our eyes? Depending on it, you may not be able to tell. Crystalline solids can, depending on how big it is, can have very straight sides to them. Like if you think of like salt, have you seen like rock salt that you use like to make ice cream? Right? It can have very clean cut sides, almost like a diamond, right? Where it has very clean cut sides, where if it was truly just amorphous, right, it wouldn't ever have that like smoothness to it. So like coal?
diamond versus coal?
Yeah, that'd be a great way of like our eyes how it might seem.
So does the pressurizing alcohol make it then crystalline, which makes it a diamond?
It changes its structure, yes.
Would ionic solids always?
Yes. They may look amorphous if it's broken up into tiny pieces, but if you could like magnifying glass even a grain of salt, it would have very clean cut edges. Yeah. Yeah, Taylor.
Would that make crystalline more brittle than an amorphous structure?
Ooh, great question. That actually would go more to what type of bond it is. Because you can't have both in one, so it would just depend. Because like, so for example, metallics, we find are typically always malleable, right? So even if it's amorphous or crystalline, they still can be shifted. So yeah, great connection. Okay, so just reviewing, just fill this in. We're going to just kind of throw out some reminders from last unit of what properties they have based on this at the molecular level. So we just said one. So metallics are that sea of electrons, and because of it, they are always malleable, right? Sometimes you need a lot of force, but you can always shift because that free-flowing sea. What were some other properties metals always have, Seth?
They're conductive.
Perfect, good. They're super conductive because free-flowing electrons, right? Good, have a smiley face for that. Give us another, Michael.
High melting point.
Good, yeah, they take a lot of heat typically because of those positive and negative forces, right? It's really hard to pull that apart to make it to melt. Good, have a smiley face for that. Okay, let's go to ionics. Okay, so ionics look like this at the molecular level, right? Positive to negative, positive to negative. okay? What were some of our properties of ionic substances? Gosh,
They also have a high melting point.
perfect, good, have a smiley face for that. High melting points, right? It's like 900 something degrees Celsius to melt salts. Because to get this guy to melt, what are you having to pull apart? Yeah, the ions, that positive from that negative, the bond itself to make it melt. Good. Other properties of ionics?
They're non-malleable.
Good, yeah, they're very brittle, right? What happens when you try to hit it? Or when you do hit it?
They shatter.
Yeah, they just shatter because of that shifting lattice. Good. Brendan, have a smiley face for that. And let's hear one more for ionics. Got another, Michael?
They're conducted like as a liquid.
Good,
Like,
yeah.
dissolve.
Once if you melt them or dissolve them, they now can conduct because of those free-flowing ions that you have. Good. So once again, form determines function, relating what this looks like causes those things to happen. Okay, now covalence, which is really the bulk of what we're going to talk about because they have a lot of variants of what can happen now. Two main classifications of covalence, and then one classification will then be broken down into three. Okay, so first, the two big ways you can separate covalence is you have things that are known as a molecular covalent. I'm going to add that word covalent on here just to emphasize. Okay, a molecular covalent, and then we also have the next one, which is a covalent network. Okay, I'm going to go to the covalent network picture first, and then we'll come back to this one. I think it makes more sense. So what happens in general in a covalent bond? Yes, I share with you, you share with me, bond is formed, right? Just like the toothpick with the Play-Doh, okay? A covalent network is literally a network of covalent bonds in all directions in massive being connected. It's not the best on yours, so maybe you can see a little bit on mine, but this is a molecular view of diamond. So diamond is just pure carbon, and diamond, you know, is like the strongest substance on Earth, pretty much, right? The reason why is because you have a covalent bond here, 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 and back. And then that one has a covalent bond, So it's like literally everything is connected to everything in the substance.
What happens if you melt diamond? Like,
I don't think we can. Because theoretically, in order for it to melt, you literally have to break the bonds themselves, right? So I don't know how or if it's even possible to melt diamond.
Diamond have a melting point?
Nope. Not at least on our planet that we can
You're
get to.
saying, like, theoretically, if you had an infinite amount.
I don't know. I don't even know if it does because of I guess everything would theoretically if you could get it hot enough, but I almost don't even know if it would melt or if it would just vaporize because once the bonds are, or just I guess it just fall
You
apart.
could turn it into a gas technically, but that would take a bunch of chemical reactions, so you technically just have to change it in order to melt it.
Yeah, so yeah, that's a good question.
Wouldn't it combust before?
That's the other problem with carbon is if you heat it, it just ends up burning. So you'd have to heat it in the absence of oxygen. What? But,
there's no internet.
yeah. So, but that's what makes a covalent network is massive interconnection in all directions. Okay. The main substances that do a covalent network are carbon and silicon. So when carbon is by itself, it does this. When silicon is by itself, it does this. And then sometimes in other situations, it does as well. So write this one down. So SiO2 is another covalent network. The covalent networks you kind of are going to just memorize because without seeing a picture, it's hard to know that it does it. Most of the time I've actually seen it where they show you a picture and then you should be able to identify from the picture oh, that's a covalent network. But last year actually on the FRQ, they threw this one on there without a picture and you had to know from memory that it was a covalent network. But another cool covalent network is also carbon, but carbon as graphite. So graphite's an interesting covalent network because it's a flat network. So in your pencil, do you want a pencil, Brandon?
It does have a melting point. It's really high.
3,550 degrees Celsius. So in graphite, which is what's in pencils now, right? It's not lead, okay? A single sheet of graphite is crazy strong because it's that covalent network. But between each sheet is just an intermolecular force. It's the friendship force. So what happens is literally when you write with your pencil, is you are laying down sheets of graphite. Like that's what writing with the pencil is you're laying down those sheets, and then when you erase it, you're just pulling them back up again. But if you can actually get a single sheet of graphite, that itself is crazy, crazy strong. Like you can't like just break a single sheet of it. But sheet to sheet, right, is just a magnetic type force. So kind of cool. Okay, the difference is with a covalent molecule is now you have a strong bond within it, right? So like in water, the H to the O bond is really, really strong. But in a covalent molecule, you now have the intermolecular force of molecule to molecule. And that's why they have typically very low melting points. Because when I melt water, what am I separating? Yeah, the waters from the waters. I'm not having to pull off, right? Like, I'm not breaking the actual bond. So that's why covalents typically melt very easily. What were some of the other properties we saw with covalents?
They're non-malleable.
They were sometimes. So covalence was a thing where every other category was like, they sometimes do this, but they sometimes do that. And because it all goes back to, well, what type of forces do they experience in between? Okay? And that's where we're now going to focus, is that in-between force of the molecules. Okay? So, big word that we will use all year long as we visualize these things is it's all about Coulombic forces. Okay? This friendship force, this intermolecular force, is a Coulombic-like force. Once again, Coulombic is the fancy word for a positive and negative attraction. Like a magnet, but it's not magnetic. There is a difference. Today we're going to be focusing on identifying them. So the goal is that by the end of class, if I give you a formula, you can tell me what type of forces that molecule experiences when it comes in contact with other ones of its kind. Right? What type of intermolecular force does it have? And then next time we'll get more into the application side of like what do those mean now, okay? Okay, first type of force, a dipole to dipole force, okay? A dipole to dipole force is a force that happens when two things are both polar. So let's review. We're getting there with the definition of polarity, but from the FRQ, some of us are still not there yet. So I'm going to say this a lot today to get it in our head. What does it mean if a molecule is polar? Izzy?
It means one side is negative and one side is positive.
Perfect. If it is polar, one side is negative and one side is positive. Why that happens is because of that shift of electrons in one direction, right? So when something is polar, what does it mean? One side is negative and one side is positive. So a dipole to dipole force is, well, this water molecule, right, is negative here and positive here because of the pull of the electrons. And so when it comes in contact with another one, the positive end of one side gets attracted to the negative end of the other. That is the dipole to dipole force. This has a dipole, this has a dipole, dipole to dipole force. Okay? The stronger the dipole moment, the stronger this force will be, which is what this table just kind of shows. Right? So this one has a really strong dipole moment, and so its boiling point is the highest because it takes a lot more energy to break it, but we'll get into that more next time. Okay? So, dipole is when?
When one side is when two polar molecules.
Good. Polar and polar, so they get attracted to each other, right? Okay, the next type of force that can be experienced is known as a London dispersion force. Okay? This is just a weak version of a dipole. Okay, so a London is just a weak version of a dipole force. Key word here is it's a temporary dipole. Polar molecules have a permanent dipole, but any molecule can have a temporary one. And we'll talk about, I'll let you fill in the blanks, but then that way your brain can listen more. Okay, what does it mean if a molecule has a dipole?
Polar.
What does it mean if something is polar? Good, one side is positive and one side is negative. So what happens in a temporary dipole is because electrons, even in a nonpolar molecule, are always moving because electrons just always move. So imagine if you guys are all electrons and I had you stand up and then I just said, okay, run around the room. And you just start moving. And then I said freeze. Is there a probability when you freeze that more of you could be over here than over here? No. So in that moment, this side has become negative and this side has become positive. But it's temporary because the electrons are not frozen. They don't ever freeze. They're always moving. So just like it formed, it can also shift and go away. This is what helps explain why even things like CO2 that have no polarity whatsoever can eventually become a liquid and a solid if you force the molecules to slow down enough, right? Like if you cool them down enough, pressurize them enough, you can get them to come together. But things that aren't polar really have no tendency to want to come together at all. Nate?
So did that happen with like argon?
Exactly, yeah. So even our noble gases, which naturally exist as gases, if you cool them down enough, they eventually can turn into a liquid and a solid. Now what's interesting is scientists have not been able to ever make helium a solid because it's really, really not prone to coming together at all. So, Michael?
How rare is the London dispersion?
So, everything does it. So it's actually really common in terms of everything has this capability of doing it. In terms of it actually causing an effect, that's probably the rare side of it. Does that make sense? So yeah, everything on Earth can experience a London dispersion force. Now the fancy word when you're justifying, so this is like, if you want to like label this as like, use this when I do the FRQ, is polarizability. Polarizability is a fancy word that describes that distribution of the electrons temporarily. So something that has very high polarizability has strong London dispersion forces. For example, bromine. Bromine is in the same family as the others, and it's not polar because it's just bromine with itself, but because of the number of electrons it has, the polarizability goes up, which is why it naturally is a liquid when chlorine and fluorine are naturally gases. And then we see the pattern continue with iodine, which is actually a solid at room temperature. The more electrons something has, the more polarizability, and the stronger the dispersion forces can be. Versus the ones at the top that only have few electrons, they have very, very low polarizability. Yeah?
So since it's temporary, does that mean that there's a little chance that it could like just all come apart and then randomly become a gas and then like become a solid again?
Probability-wise, I'd say yes. Now they often say they kind of cause like a domino effect, right? Because if we're a molecule and we all of a sudden have a negative one side and a positive another side, a molecule next to us, we can kind of like cause that temporary dipole. But I would say, yeah, probability-wise, yeah, it could.
So iodine's a solid, so does like the iodine we use in pH tests, is that like actually combined with something else?
Yeah, I can't remember what it is, but it's not pure iodine. It's an iodine compound. We call it iodine just because it's like the main part of it, but yeah. Same thing as like chlorine in a swimming pool isn't like pure chlorine gas, it's a chlorine compound. So yeah, good connection. Robbie, you had something?
So with that, if they have a London dipole, they force the other atom to have?
Yep.
Okay.
But then once again, there's nothing that's truly holding it there, so it could easily break back the other way. So, Questions on a London dispersion force? Now my favorite definition of polarizability, and I should pull it out of my cupboard, I have all my college textbooks in there, but in one of my college textbooks, the way they defined it for polarizability is they call it the squashiness of the electron cloud. Because if you think about it, so look at this picture right here, imagine it being a perfect circle before. Polarizability is when the electrons shift, and so the cloud got squashed. Versus if they were equally distributed, it would stay like a perfect sphere. So I don't know, that always helped me visualize.
I thought it's in the college textbook.
And that was my favorite part too, was studying in a college textbook. So. Okay, our last type of force is an extreme dipole. So they're all dipoles, but you just have a temporary dipole, you have the regular dipole, and now we have the extreme dipole, which we call a hydrogen bond. Okay, still a dipole, so what does it mean if something has a dipole? Good, one side's positive and one side's negative. This one is just extreme, so it's really positive and really negative. Okay, fill in the blanks and then we'll talk about why. But don't lose that definition of it's just all about dipoles. This picture's on your page, right? That got printed, that water molecule. Okay, everybody ready? Get your pencil, we're gonna draw on this image right here. Okay? Okay, so little water molecule, your little Mickey Mouses, right? Okay. So first off, just to remind us, why does it look like Mickey Mouse and not like a straight line? Good, right? So you have two lone pairs pushing these down. Now, why is it polar? Good. So the electrons are being pulled this way because of electronegativity. And then since they're angled downward, it's going to make this side of the molecule negative and this side positive, right? Polar means one side is negative and one side is positive. Now, the reason why it's an extreme dipole is there's two factors. One is oxygen, nitrogen, and fluorine, so NOF, those three, are very small and have really high electronegativities. So when they pull the electrons away, they do it like almost too ionic, like I'm going to take it from you, but it's still covalent. So that's the first thing of what makes it super strong, is you get a super strong, so kind of bold this arrow, super strong pull that way. Key thing is N, O, or F do this. The second reason is that it's bonded to hydrogen. It's small and only has one electron. If you pull the only electron away from an atom, what is left? Just the nucleus, right? And so not only is it positive, but we get a super positive tail. So you get an extreme positive and negative, which then results in a very strong force between them. So this is the hydrogen bond, right? This is a covalent bond. Hydrogen bond is the force between two molecules. Tanner?
So is this kind of one of the reasons why like electricity goes through water pretty easily, or is that more like you talked about it with metallic?
Yeah, so it's not, because remember with water, it's what's in it.
Yeah.
But because of it, water brings things into it really well. That's why water can dissolve. They call it a universal solvent because it can dissolve almost anything. So yeah, harsh.
So if you take away an electron from hydrogen, like, is the electron cloud still there? Or is it just the nucleus?
I mean, technically it's not totally taken away, right? Because it is a shared covalent, but it is mostly empty, yes. Jake?
Hydrogen bond isn't technically like a bond, it's like
Very good. Yeah, it's one of there's a few pet peeves I have with like how they named things, and this is one of them, because it's not a true bond. It's still just this to this. This is the hydrogen bond. But it's not a real bond, but it is the strongest of the three forces, so I'm guessing that's why they put bond with it. But I still don't love it because it is deceiving. Now,
Dodge Collins to check out.
yes. So this chart actually kind of shows that. Oh, I'll come back to this here in a second, but just to answer what Jane was saying. So this shows you, this is the strength of a true covalent bond, right? And notice the scale numbers are not to like proportion, right? Because this is like 1,000 and this is like 20. Like they're not spaced accordingly, right? So to break an actual covalent bond is super, super hard, right? Like if I want to take the H off of the O, I have to send electricity through the water to do that, right? Versus to break the hydrogen bond, well, I break the hydrogen bond anytime you jump into a swimming pool. But that can feel quite painful at times if you don't jump right. Right? Like literally belly flopping is because the water molecules are playing Red Rover against you. And I don't know who wins, I guess, but like you're feeling the force of a hydrogen bond when you land on water, right? So it is strong, but yes, it's not a true bond at all. Okay? Okay, let's go back to this and summarize our three types. Okay, so here are the steps to identify a force. Okay, so this is what we're going to be doing on our homework, is identifying what forces something has. Now, if it's ionic, it just has ionic. If it's metallic, it just has metallic. If it's covalent, you then have to sort out, is it a network or is it a molecule? And then if it's a molecule, which of these does it have? Now, the first one, everything has London force. So the question is, does it have a London force? If it's covalent, the answer is yes. All covalent molecules can experience a London force because they all have electrons that can temporarily shift. Okay? Next step is, you gotta know if it's polar, so we have to have the Lewis structure. Because you can't know if something's polar without drawing, or at least visualizing what it looks like in 3D. If it's not polar, it only has London. If it's polar, it now has dipole as well. These forces are additive. If everything has London, so some things can have London and dipole. Now, if it has dipole, check to see if it also has hydrogen. But notice, if it doesn't have dipole, it can't have hydrogen, because hydrogen is the extreme dipole, right? But if something has hydrogen, it's going to have all three, right, by default. So for hydrogen bonding, we're looking for a direct connection of H to NO or F.
Tyler, is nitrogen, oxygen, and fluorine, are they the only ones that can hydrogen bond?
Yes. Yep, great clarification. Yep, those are the only three that do this extreme shift of electrons.
Why is that?
Just because of their very, very high electronegativities and small size. Because like chlorine has a pretty high electronegativity too, but because it's bigger, it can't get as big of a shift. Yeah.
So like helium and neon don't bond with anything, so they don't bond with each other either. So are they just molecules that just kind of float around?
Yeah, so they're technically like individual things. Now they technically can experience London forces, because even they have their own electron cloud. So that own electron cloud can still do the squashiness of polarizability, but that's why they're all gases at room temperature. And to get them to be a liquid is like, I mean, I think it wasn't until you got down to like 2 Kelvin to get like helium as a liquid, which is like crazy. So, yeah. Okay, let's do these ones together, and then I'll have you try the others for a smiley face. Okay, this is exactly what homework 3.3 looks like, okay? All right, so step 1, you've got to determine what type of bond is happening within it, because then you can sort out what type of force it would feel. So, reminder from last unit, how do I know what type of bond something has?
The periodic table.
Perfect. I go to the periodic table, I find nitrogen. Is nitrogen a metal or a non-metal?
Non-metal.
Good, so nitrogen is a non-metal. Hydrogen is a non-metal. Non-metals with other non-metals is a covalent bond. Okay? So, if it's a covalent bond, then yes, I'm going to need a Lewis structure. If it's not covalent, Lewis structures don't apply. So it looks like this. I'm just going to kind of go through it quickly just to focus on the intermolecular forces side of it. But if you need more help with Lewis structures, come see me. But on the FRQ, that was actually something like majority of us are really good with Lewis structures, so that's a good sign. Okay, so we got our Lewis structure. So now, since it's this, it only can be these. These don't apply if it's not, because those aren't covalent. Okay, is it a covalent network? Nope. If you can draw a Lewis structure of a singular thing, it's not a covalent network, because covalent network is everything is connected in thousands of ways. So it's not this. So that means we look through these. All right, does it have London forces?
Yes.
Why?
Because it's covalent.
Because it's covalent and everything covalent does. How do I know if it has dipole to dipole force?
If it's polar,
Okay, so is it polar?
yes.
Why?
Because it has a ghost.
Yes, we got a pyramidal sheet because of that lone pair. All the electrons are being drawn towards the nitrogen. And so we end up with, right, our positive side and our negative side. And a polar molecule is something that has a negative and positive end. So, since it's polar, yes, it has that force. Does it have hydrogen bonding?
Yes.
Yep, because we look for hydrogen connected directly to N, O, or F. Questions so far? Okay, let's do the next one. So the next one is just Kr. So it's just Kr by itself. So in terms of bonding, you can think of like a Kr interacting with another Kr. What type of bond would you maybe say that would be? Covalent. Okay, you don't really need to draw a Lewis structure because it's just a Kr, right? So can it experience London forces? Yep, because everything can. Everything has electrons. Dipole force? Is something by itself going to be polar? No way, right? Because polar means it's shifting the electrons, which means if it doesn't have this, it can't have that, and these are, I don't know. Questions? Okay, HCl. What type of bond is it? Also covalent. The Lewis structure looks like this. London forces? Yes. Is it polar? Definitely, right? Because there's only two, and the chlorine pulls the electrons, so definitely a negative and positive side. Hydrogen bonding? No, so be cautious, right? There is a hydrogen, but it doesn't have N, O, or F, right? Nope. Yeah.
So if it has dipole attractions, does it mean that it can have a different network?
Yes. Yeah, pretty much if we box this, it's just going to be that box. And you wouldn't worry about any of the others. Okay, last one. Zinc oxide. Which bond is it?
Ionic.
Yep, so it's ionic, so that means over here it's just that one. So ionics just have ionic.
So doesn't it have the London forces?
Great question, Michael. It actually doesn't now. So why would an ionic one not have polarizability? And what's the lattice made of?
Is the ions.
It's full positive, full negative. So you don't, because in order to have the polarizability, you're getting a partial negative and partial positive, but ionic is already just negative and just positive. So yeah, great question though. Okay, any other questions before I have you try some on your own?
What was a metallic bond? Would it have London forces?
No. So same thing, metallic doesn't. It's just metallic bond. Okay, try out the rest of the table. You can talk with your table buddy if you want, or try it on your own, and then we'll check it for some smiley faces, okay? All right, ready, set, go. And I'll start passing back your test, actually, why.
Just got one of the forces and all those factors.
What's this one?
Potassium, magnesium, or sorry, manganese metals.
Is there a reminder? I beat the reminder. I reminded myself. Did I miss anybody? Did everyone get their test back? There you are. Oh, Brandon, I have yours too, actually.
How do you tell if it's a covalent?
The annoying part is it's, you definitely like be able to, it shows you a picture, you should be able to identify like, oh, it's bonding in all directions, so it's a network. Outside of having a picture, memorize, they're rare, so kind of just memorize the few that do it, so like pure carbon, pure silicon, silicon dioxide, like the main ones, I just kind of have them memorized. If it's not one of those, then don't assume it's a network. Yeah, there's a few on your homework I threw on there, like, but I just like dived in. Like, yeah, that's the annoying part. Is it's kind of there's no. Because even silicon dioxide's a tricky one because a lot of people would look at that and be like, oh, I can draw an individualized like thing that looks like CO2, but it actually doesn't do that. It actually. Great question though. Harsh. What type of bond? Ionic. Because potassium, anytime you have a blend of metals and non-metals, it's always ionic. No matter what like ratio it is, just anytime there's a mixture, it's ionic. All right, I'll give you 1 more minute to finish up your table, and then we'll check it for some smileys. Yep, and then, yep, so just, and then just a little bit of reading about IMFs. Okay. I'm gonna go through it just so we can make sure we're on the right page before. So let me know if you got one wrong and you don't understand why. In order to get the smiley face, though, you have to have labeled like the whole theme correctly, right? So if you like checked a box you shouldn't have checked, or you missed a box you should have. Okay. Okay. So F2 is covalent. You don't really need the Lewis structure. You probably can just visualize it with itself, but if you were to draw it, it just is this. And then the only force it has is London. Questions on that one? Okay, the next one is ionic. And so it just has ionic. Alright, the next one is covalent, and so this one you do have to draw it out because you need to know that it ends up being like this, which is important because we know it has London, but then because of this, is it polar?
Yeah.
Yes, because what shape is it? Bent, right? Looks like, because that lone pair. And if you don't draw it and you just think it's linear, then that messes up. So yep, it is this, but then it doesn't have anything else. And then the last one is just metallic. Did you put X's on all the others? No. That's funny. All right, so your homework looks just like this table, and then just some reading, but then the big thing is your best for lab is due tonight. So if you haven't turned that in yet from before the break, it's like that white tables upon tables of Lewis structure and 3D shapes.
I just did that during one of my classes.
We got it like the Monday before fall break. Yeah, but that is due tonight, and then I know Wednesdays are always crazy. Like, oh, now we got to transition. Oh, I guess we don't need to film everybody leaving.